At this point, we have a pretty good idea, I think, about the major features associated with what viscoelasticity means, and eventually we even have a model, a relatively good model, with which we can reproduce those main features. Remember, viscoelasticity is serving simultaneously not only as a topic that is very important for polymers, but also simultaneously as a way to demonstrate the influence of the strain rate on material behavior, in particular in this case, material behavior that is not elastic. In this case, it is viscoelastic. Likewise, it's also important, by the way, for plasticity, but we're sort of modeling those in the ideal case of a viscoelasticity where it really finds a very clean application. Now, similarly, now we want to go back to a very early remark that we made in the stress strain curve, and where we said that the temperature also influences the material behavior, in particular inelastic material behavior. We already know that it does influence the elastic material behavior through the thermal expansion coefficient, but how about inelastic behavior? Again, we're gonna address that question in the context of viscoelasticity. And so this takes us to the step 7 of our discussion, where we incorporate temperature effects. So here, the temperature is going to be indicated with, as we did before, through T. And we are going to start off by recalling the standard linear solid relaxation behavior, which we indicated as for a given strain that is a constant, right? We impose a certain amount of deformation and measure the change in the stress with time. If it's a purely elastic solid, then there is no change. It's a immediate response to the strain, and then afterwards strain is a constant, stress is a constant, but not for a viscoelastic solid. The prediction of that relaxation behavior with the SLS model is as such, where there is a E infinity, that's the spring material constant of that spring in parallel with the Maxwell element, and then there is another Young's modulus associated with the spring that is in series with the dashpot, and that Maxwell element has a time constant that is associated with it, which is equal to tau, the relaxation essentially time that is associated with that Maxwell element. So now what I am going to do here is I am going to just divide through epsilon 0, because the magnitude of epsilon 0 will only scale the magnitude of sigma, but not alter its general time-dependent behavior. So I'm just going to divide through epsilon. So I'm going to say that the magnitude is irrelevant. Irrelevant to what? Irrelevant to the time variation. And I'm just going to divide through epsilon 0. And I'm going to call that ratio, in other words, the ratio of the stress variation to the amount of constant strain imposed. We're going to call that a function g of time, obviously. And so that's sigma of time divided by epsilon 0. Notice that it has units of time. It has units of megapascals if stress is also megapascals. And it's called the relaxation function. And it serves almost like a modulus, right? If the stress did not vary with time, this would be the elastic modulus. But now it changes with time, so it's a function of time, hence the name relaxation function. It's a function that's associated with the relaxation behavior. And that function is said to be the signature of viscoelastic behavior. So it is really a signature in the sense that if I like to learn about the behavior of a metal under slow loading conditions at, say, a given temperature, what I would do is the stress strain curve. And I would do a test, generate that curve, and I would extract a lot of information, the Young's modulus, the yield strength, ultimate strength, etc., all from that curve. So the stress strain curve, if you like, is the signature associated with, say, a metal's plasticity, or for that matter, some polymer's plasticity. If you are looking at a material behavior where plasticity is perhaps not of significant concern, such as in the case of this viscoelastic foam, but instead the deformations are governed by, the mechanics is governed by mostly reversible deformations, reversible in the sense that you can recover all of the deformation that you impose on it. Those are governed by viscoelasticity. Then the signature of this material's behavior is associated with or given by the relaxation function. Okay, so that's the signature of a polymer, if you like, if that's what we have as our viscoelastic material. So now that is a function that has an exponential variation. We're going to go ahead and plot it. But for SLS, we therefore notice that GT is a function which has the explicit form E infinity plus e to the minus t over tau. So there are two characteristic points associated with that curve that we're going to draw. So first, the value at time equals 0, and we know that the material starts off always as stiff and then with time under relaxation becomes softer in some sense. And so at infinity it goes to a smaller value. So that's the start off modulus and that's the ending modulus of the material, if you like. So those are the points that we're going to connect smoothly with an exponential variation. So that variation, by the way, is best shown on a log-log scale. So that's what I'm going to draw here. I'm going to draw the relaxation function on a log-log scale. Okay, so remember and keep this in mind, this is going to be a log scale, and so is that, because that's where you see the characteristics of the relaxation function much more and clearly. So we'll go ahead and draw that function, and it turns out that it looks like this. Okay, so as we indicated before, the start-off point is the point that is associated with G of 0, which is E infinity plus E. That is the stiff start, and the end point is, I'm using the same type of dashed and solid green lines that I used before. This is the end. It is the soft ending, which is E infinity. Okay, and now we're talking only in terms of what is intrinsic to the material behavior. Again, stress is not quite intrinsic because it's scaled with respect to epsilon 0, but the relaxation function is intrinsic to the material. It's, if you like, a material property. So the horizontal axis is time, and it is seconds on the log scale, and the vertical axis is the relaxation function in terms of MPa. Now I'm just going to write here some indicative values of these scales that we are showing on the plot. And so this value here could be as high as 1000, and this value here could be as small as 1, and the time could be as small as 10 to the minus 7, and it could be as large as 10 to the 4 or even much larger. Okay. But notice that this is of the order of hours, and then we rapidly decrease towards the order of seconds, and then further rapidly decrease to extremely small time scales. So that's what the curve looks like on the log-log scale. So there's a reason why we're plotting it like this. And one reason is exponential is very rapid in terms of the linear scale in time. Variation is very rapid. We wouldn't be able to see this characteristic curve. And two, it's important so that we can, let me say, interpret temperature effects more clearly. Now, that's what the curve is. So now what that curve tells us is, right, it starts off very stiff, and then when the time passes, then the stiffness decreases, and hence for a certain strain the stress decreases, and then eventually it ends up and it saturates to its final behavior. So this is where all the action takes place. Initially not so much. So in other words, in the very first few, let me say, time intervals associated with that scale, not much is happening, and then all of a sudden quick action, and then again not much is happening, and then it goes like that forever. If you like, it goes like that forever in the reverse direction, but those are extremely small values that may not be of interest to us. So that, by the way, is always an important remark. So we have to eventually identify our region of interest on the scale. We might be interested in an application where the time variations, let's say the period of a motion, is of the order of minutes. Then hours is not of interest to me. I'm in that region. We might be interested in an application where we have an extremely high frequency loading that is less than, with a frequency that is, or period that is much less than a second. Then I would probably be over there. And this is the type of modulus that the polymer is displaying, just as a way of motivation, right? So this thing gives us some information about how fast the polymer is responding to loading at, if you like, different frequencies almost. Okay, in some sense, we're gonna quantify all of that further, at least in our exercises. Now, I'd like to do a very small conceptual exercise at this point, and what I'd like to do is the following. I will go ahead and do a simple experiment where I'm going to take a polymer, okay, which is going to be viscoelastic. This is one such polymer. And I'm going to do a test. So this test is going to be a test which is a relaxation experiment. So I'm going to push on the polymer, and then I'm going to monitor the stress. Now, but I'm not going to monitor the stress forever. If I do that, I will get that curve. I'm going to monitor the stress by essentially compressing it, right? In this case, not pulling, compress it, but keeping that load constant. And then I will reach a certain time. So I will start the chronometer. So that's 0 seconds. I will compress, and then I will start counting, say 1, 2, 3, 4, 5, and then I will measure the value of the stress and plot it on that scale. Okay, so I'm not going to wait forever. I'm just going to be interested in the value of the stress at a certain point. And let's identify that point with some reference time. Let's call it T reference. Okay, so the value of the stress that I measure at T reference is going to be, in this case, that value. So the stress is going to be the value of the strain I impose times the value of the relaxation function at that time. So that's going to give me the value of sigma at that T reference point. Now, that T reference point is just something that I pick arbitrarily. Now, before I move on further, is this T ref necessarily a characteristic response time of the polymer? Well, not necessarily so. We've already mentioned what the characteristic response time of the polymer is. It's called the relaxation time. It is a time beyond or near which we see significant changes in the material response. So the T ref is something that I choose arbitrarily. It could be here, it could be there, it could be somewhere in between. But the relaxation time is something that is essentially intrinsic to the material, because remember, it's the ratio of the Young's modulus to the viscosity to the Young's modulus of the material parameters that appear in the Maxwell element. So therefore, I can, remembering its meaning of a significant change in the response, I can, if you like, put that value here as well. That value probably, okay, probably would go somewhere, let's say, there. Okay, so it's probably larger than Tref, and let's call this value tau. Okay, so again, that's the meaning of tau. It's the characteristic response time, significant decay in the stress. It hasn't, or the relaxation function hasn't really decayed, but has significantly decayed. So that's indicative of the relaxation time, and it reflects this meaning. But this is some arbitrary time. And now let's say that this experiment was done at a certain temperature. Let's say at a reference temperature of the medium. And now what I will do is I will carry out the same experiment with the same material. So in other words, I will take it, do a relaxation experiment sort of, compress it, count 1, 2, 3, 4, 5, and measure the value of the relaxation function, but this time when this test is carried out at a different temperature. That temperature could be higher or lower. Okay, so we'll start off at time equals Tref. I'll measure the value of the relaxation function and also plot it on this log scale. And the only thing that changes is the temperature of the medium or the temperature of the material. So now let's first try to imagine what might happen. Well, we can try to imagine what might have happened based on our experience in daily life. And our experience indicates that if I take something that displays significant viscous behavior, let's pick for instance honey, right? And what happens is, if I put it into the refrigerator, I can easily observe that the way it flows becomes a lot more viscous. And we can translate that observation into the following statement. If I want to pour it, if I want to empty the, let's say, honey jar, it takes a certain amount of time, right? When I cool it down, it's going to take a lot more time. So in other words, the time it takes for the material to respond to the loading, in this case gravitational loading, to pour the honey out of the jar, it's going to take more time. So the response time is actually decreasing. So the response time is, right, tau is equal to the ratio of the viscosity to the Young's modulus. Now, the Young's modulus is, in our model at least, it's something that possibly is not going to depend on time. That's going to be our idealization, okay? I'm going to comment on that shortly, okay? Okay, so in other words, if we have a pure elastic solid, whether I cool it down or heat it up, it's not going to change its Young's modulus significantly. This is within reasonable temperature changes, is actually a very physical statement. So the Young's modulus might change with temperature, does change with temperature, but within reasonable changes to the temperature, it's not going to change much. But it turns out the viscosity is not like this, just like I already expressed in the honey jar example, right? So now the time constant is increasing with temperature, okay? And therefore, what must be happening is the value of the viscosity must be increasing with time. So what changes here is the viscosity in our model. Okay, and eventually that's the way we're going to reflect temperature effects onto the viscoelastic material by making either the viscosity or the relaxation time somehow a function of temperature. Again, remember the honey example. Another example is, if you like a rubber band, right? A rubber band It's a slightly different example. It's not quite the same thing, but really if you were to do a measurement, at least qualitatively, we know that polymers, through the rubber band example, respond strongly to temperature effects. It can easily deform when it is subjected to a temperature that is, say, at room temperature, but if you put it into the freezer, take it outside, well, something happens. It becomes very stiff. Now, it's not exactly the same, but it's a similar observation that eventually we extract out of that example as well. So now what we've observed is from our honey jar example is that the relaxation time is going to increase if the temperature decreases. So if we go back now and I ask you, well, what should the corresponding relaxation time be if I start this experiment and I carry it out at a temperature that is, right, 1, 2, 3, 4, 5, I'm going to measure the corresponding relaxation time and I want to put it here at a lower temperature and hence my blue pen. Shall I put that at T-ref above or below? Right? So what's happening is, right, the relaxation time is shifting to larger values. So in other words, for significant decay to occur, it's going to require more time. The relaxation time will shift right, and therefore the time it takes for the material to decrease in the relaxation modulus should actually, if it's going to decrease by the same amount, it's going to take more time. Or if I give it the same time, the amount of decay, in other words, the amount of response will be less. It's taking its time. So if the temperature is lower, the data point I measure will be higher. And in fact, if I go ahead and try to draw this whole curve, okay, it turns out that the curve is actually very similar to the original one. It just looks as though you've somehow taken the black curve at the reference temperature and shifted it right in some sense. So this is the same curve almost, except that the temperature has decreased and therefore the relaxation time has increased, or the viscosity in some sense has increased. So likewise, if you now increase the temperature, the material's characteristic response time actually is going to shift left, so it's going to respond much faster. So at a given time, the amount of decrease in the relaxation function will be less and will be more, and therefore if I draw the same curve, it's gonna look shifted to the left. Okay, so that's the way the relaxation function looks when the temperatures increase. As a result, the relaxation time is decreasing, and because the viscosity is decreasing, right? Okay, so that is something that perhaps aligns with our expectation based on simple experiments, but certainly is supported by experimental data. When you do the experiments, this is also what you observe. Now, one comment again. So I already said that E on our expectation, based on our expectation, it shouldn't change much. In reality, does it really change? Well, it turns out that it might change when you change the temperature. In other words, these limits are sensitive to the temperature to a certain extent, but we are going to omit that change in our simple discussion, which is, again, a very, very good point to start from. So what we've observed is relaxation, to summarize here, is faster it is faster or slower at faster if the temperature is higher, slower if the temperature is lower T. Okay, relaxation is faster if the temperature is higher, slower if the temperature is lower. Now, that's a nice experimental input. Now, what we're going to do is we're going to do something that is going to build up on this picture. And now I'm going to draw here a new plot. And on that plot, the horizontal axis is again going to be the relaxation function, hence MPa, and it is again going to be the log scale, okay? But the horizontal axis is going to be the temperature. You can pick the temperature if you like Kelvin or degrees Celsius, doesn't really matter much. And eventually the scale, the horizontal scale, however, remember, is not going to be, in this case, remember it was log, in this case it's not log. Okay, so I'm highlighting that so that the difference is clear. This is a standard linear scale, this is the logarithmic scale. Okay, so not log. Let's put that in parentheses. So the temperature change here depends on the material. I'm going to comment on that, so I'm not putting any indicative numbers here, not yet. Well, the question now is, suppose I take these points and try to put it on the map over here. So first of all, I have different temperatures. I have a point that is associated with the green temperature, the temperature that's associated with the reference point, which is the room temperature, say. Okay, so that's a T. And then I have the blue colder, and then I have the black. Okay, so for every value, I'm going to plot a value. And in fact, I could do that for many points for Tref. It's always at Tref, so I'm looking at that line. So this is at T equals Tref. I could have chosen a different Tref, but I'm just going to pick that point to be generic. Eventually, the curves will look similar. And so at Tref, I'm going to pick many points corresponding to many different temperatures, and let's see what we get here. Now, this is not necessarily something that's intuitive. In fact, not at all. Again, it's an experimental result. And what we see here is that eventually the curve, interestingly actually, looks almost identical. Okay, so let's smoothen that part out as much as I can. All right, good. So in particular, the starting point is again E infinity plus E, which means that if the temperature is very low, okay, if the temperature is very low, then it's so low that the response time is so high that the material will take forever to start to relax, and therefore when the temperature is very low, you're close to the upper bound. On the other hand, if the temperature is very high, then the material relaxes so fast that it reaches the final value very quickly. That's why if the temperature is very high, then you already reach the final limiting value, which is E infinity. Okay, good. So I understand what is going on here, and you see the curve looks apparently, based on experimental observation, very similar to the original curves that I have here. Now, it turns out that just like we have a characteristic response time, there is a characteristic temperature here. And that characteristic temperature, let's highlight it. That characteristic temperature is a temperature that similarly sort of finds some midway in some sense through the upper and lower bound along the way from the top to the bottom. It's a point where significant changes are taking place in the relaxation modulus that I measured at a given T reference. So let me go back. This is G of T reference. Let's correct that because I'm measuring at T ref, okay, and the variation is due to the temperature itself at that given measurement time T ref, and there exists a certain temperature near which significant changes are taking place. That value of the temperature is called the glass transition temperature, TG. And its value, just like the characteristic response time tau depends on the polymer, it depends on the values of eta and E that is associated with that polymer, let's say. The glass transition temperature is also a polymer property. So different polymers have different values. So they could be very different. So it could be, for instance, about minus 50 degrees Celsius for natural rubber. Or it could be as high as plus 70 degrees Celsius for something like PVC that is typically employed, okay, in daily life, right? So the range could be very, very high. So the variation is with respect to the glass temperature, glass transition temperature, and on the other hand, that variation is not a range that is very, very different from polymer to polymer, at least certainly dependent, but we can write some characteristic values. So let me correct that as blue and this part as green or red. Okay, so this range is about 10 to 50 degrees Celsius or Kelvin for most polymers. Again, does depend on the polymer, but that's a good range. So on the other hand, now I've divided that plot into 3 regions, okay? And now those 3 regions again have to do with the variation of that curve. So first of all, if I am to the left of the blue line, then there isn't much happening in the value of the relaxation modulus with respect to temperature. The polymer just takes the same value of the modulus and it seems to be insensitive to the temperature. The temperature is so low that the material is going to take forever to relax. Remember, here in this region, the relaxation time is very, very high. So here we call such a polymer glassy, and it acts very stiff. And on the other hand, if the temperature is very high, the relaxation modulus is so low, the relaxation function value is so low, in fact it reaches its final value so quickly because the relaxation time is so low, that the material always acts very soft. We call such a material rubbery. Where it acts very soft. So rubbery is in that region, glassy is in that region, okay? Now, therefore, in those 2 limits, there isn't much happening to the polymer behavior. If the temperature is very, very high, it's always very soft. You only see that picture. And on the other hand, if the temperature is very, very low, you only see that picture. It's very stiff. So it acts effectively as an elastic material, which never shows any viscoelastic material, very, very stiff. Or it acts as a very soft, rubbery type material, which acts very, very soft. If you're in between, however, that's where all the action takes place. Just like being in the range of the relaxation time, where all the action takes place and not so much happens either to the left or very much right of that region. So these regions are just indicative. I'm not putting any values, but let's just note that the intermediate region, this region, is where the action is taking place, and that's where we observe strong viscoelasticity effects. So, well, alright, so much for a lot of talking. Now, eventually, I'll go ahead and mention the practical relevance of all of this. So, first of all of this behavior reflects onto the material behavior. So, if we take a material such as this, which is made of some type of foam, but it's ultimately based on a polymer, well, I don't see any significant viscoelastic material behavior here. Because it seems at room temperature, this thing is relaxing extremely rapidly. Okay? If it was not relaxing at all when I pull my hand, it would take forever to relax. That's not what's happening. It's relaxing extremely rapidly. So what does that tell you about the glass transition temperature of this polymer? Do you think it is much lower or much higher than the room temperature? Well, the answer is room temperature must be here so that it relaxes very fast to the final value. The relaxation time is very, very low, and therefore glass transition temperature must be very, very low. And that's the case for natural rubber. Natural rubber is, let's say, think of a rubber band, for instance, although it's not exactly natural, it's very easily deformable, very soft. So the glass transition temperature is very, very low. But if you take the same thing and put it into the freezer, now it becomes very stiff because you're decreasing the temperature of the medium, and the modulus, the stiffness, appears to increase because you're decreasing the temperature. It's the same material, it's just that the way it responds is changing. So similarly, if I take this pencil, seems to be made of a very hard material. Well, what would you say about the glass transition temperature of this material with respect to the medium? Well, probably it has a glass transition temperature that is much higher than the room temperature, because this is something rather hard. If it had a glass transition temperature which is much smaller than the room temperature, it should be close to that limit. And in that limit, I know that the moduli are actually very, very low, right? This number is 1 MPa, should be very low. But this is not a very soft material, it's rather a stiff material. Now, on the other hand, if I take a material like this, so one example I gave you was sort of rubbery, the other one was glassy. Now, if I take something like this, well, where does the glass transition temperature of this thing lie? Well, probably near room temperature, because I'm observing strongly viscoelastic material behavior, strong time-dependent effects, right? Time-dependent effects easily at room temperature, and hence this material is governed by this region, must have a glass transition temperature that is close to the room temperature. So that's how you can practically reflect all of those observations into some daily life experience. Next, what we want to do is we want to take these things, these observations, and now we've talked a lot about temperature behavior, temperature influence. We want to quantify that influence based on these plots.